Please meet our speakers from Amazon Web Services. Giorgio Bonzi, who is a Senior Database Specialist, SAEMEA, and Tony Mullen, who is a Senior RDS Specialist Solutions Architect. A couple of words about them. So Giorgio focuses on Oracle and Postgres and helps customers design, deploy, and optimize relational database workloads on AWS. And Tony brings over 24 years of experience working with databases and specializes in PostgreSQL, having spent the last 7 years at AWS focusing on all things data. And the topic for today is going to be best practices for queuing vector data for GenAI apps in PostgreSQL. A reminder that you can ask our speakers questions through Slido, so we will be able to go through them, discuss the questions, the topics, and of course, you will have an opportunity to win a prize from the NAX. So, Giorgio, Tony, I welcome you guys to our virtual stage to share the best practices, your experience with our participants. Welcome.
Hey, how are you doing?
Hi, everyone. It's a pleasure to be here today.
Yeah, looking forward to it. Looking forward to sharing PG vectors to you.
Okay, thank you, Tony. So thanks for joining this session today, and we will cover a very popular topic in the industry right now, the vector data and vector databases, and their role in generative AI application. And specifically, we will focus on similarity search and retrieval. But I start quickly introduce myself. My name is Giorgio Bonzi. I'm a database specialist solution architect, and I'm part of an EMEA team. We are focused on fully managed relational database service, so RDS and Amazon Aurora specifically. And today I'm here with Tony. We are part of the same team, but same EMEA team, but we are located at the opposite side of EMEA because Tony is based in UK and instead I'm based in Italy, in Milan. And probably you will recognize it also from our accent, but it's not exactly the same. But Tony, please let quickly introduce yourself and let's kick off the session. We will see you
sure.
later in the second half.
Hi, everybody. Yeah, as Giorgio said, we're in the same team, working in a worldwide specialist organization, helping people with, specifically for me, I specialize in Oracle and Postgres. I've been with AWS now for 2 years. Pre my time at AWS, I was an AWS user myself for around 7 or 8 years, working on Oracle, Postgres, and kind of all things data, as we said before in the introduction. So today, as Giorgio says, we're going to be looking at best practices for querying vector data in GenAI apps in Postgres, and we've got some nice demos for you so you can see it in action. So let's get started. Okay, so the agenda for today will be, firstly, we'll be discussing retrieval augmented generation, RAG. Next, we'll see RAG in action with a demo. We'll be using Amazon's Bedrock knowledge bases and Postgres Aurora. Next, we'll then discuss Postgres as a vector store. And finally, we'll be discussing Amazon's Aurora features with vector queries. So what is RAG? So RAG, retrieval augmented generation, is a process for retrieving facts from knowledge bases to ground LLMs with up-to-date, accurate and insightful data. And we supply this by a prompt. So just give a little example. So in the example here, we've got a store which happens to sell vases. And what we're wanting to do is we want to ask some questions around some of the products we sell in our store. And if we just ask one of the foundational models, an example like what we have on the screen, how much does a blue elephant vase cost? We're probably going to get an answer like, sorry, I don't know, or potentially we're going to get an incorrect answer, something what doesn't match what our product catalog is, because that large language model, the foundational model, is not aware of what our data is. This is where knowledge bases comes in, where you can have your product catalog and your product data and your price data. fed into the large language models. So the foundational module, the large language model, understands about your product's data. So in that question we asked before, how much does a blue elephant vase cost? We'll get something which represents a bit more what we would like to have. A blue elephant vase typically costs $19.99. So you can start to see how providing your product data information into a knowledge base, you can start to see how you can really leverage foundational models. So really what we need is a common interface to be able to take our data from our databases and product data and be able to give it to a large language model to use. Now, this is where the vector data type comes in. And it's really a bit like a large array, a big list of numbers, which you can see on the right-hand side. And for the purposes of generative AI, the raw data goes into something called an embeddings model. Now, we're going to be using Amazon Titan embeddings in our example today. And what we do is we pass our product information, so our blue vase, our red chair, whatever our product information is, we pass that into the embedding model. The embedding will create a large number, a vector. And what we can do then is once we have those vectors, we can start to use them in other parts of generative AI. So particularly today, we're going to be looking at similarity search, which we'll be going throughout the slides today, and we'll see it the demo in action as well. So one thing what's worth noting as well is the same embedding model needs to be used for the data you're putting in as well as the questions you're going to ask, so it can interpret the right vectors between the two responses. So the simplest way to build and scale generative AI applications is with Amazon's Bedrock. If you're not aware, it's a fully managed service that offers a choice of high-performing foundational models from leading AI companies. And it comes with a broad set of capabilities for you to build generative AI applications. So with Bedrock, you can experiment with a variety of foundational models, and you can customize them privately with your data in your account. So knowledge bases for Amazon Bedrock is a fully managed retrieval augmented generation workflow. So it vastly simplifies your retrieval augmented generation experience. It manages ingestion, retrieval, prompt augmentation. So you simply point the data. In our case, it's going to be an S3 bucket in our demo. And Bedrock will fetch your documents and it will convert them into embeddings, as we talked about earlier, and then it will store them in your vector database. And we'll see this all in action as well with the demo. It kind of bring it to life a little bit, so you can see kind of, I guess, a little bit of how the magic works and how it's stored in the data store as well. So some of the vector databases for Amazon Bedrock we have on offer. So there's OpenSearch Serverless, Redis Enterprise Cloud, Pinecone, and MongoDB. So today we're going to be looking at Amazon's Aurora and Amazon's Aurora Postgres. So as I said, the demo is going to be retrieval augmented generation, and we're going to be using knowledge bases for Bedrock and Aurora Postgres PG Vector. I will share the link for this. This is one of our workshop studio demos, so it's something you can try yourself as well. You can always reach out to your account team as well, and they could look to potentially set a workshop up for you to go through this in action as well. But before we do the demo, I think it's quickly nice to show how the vector embeddings are used and how the RAG workflow works. So let's take a document. So in our case, we're going to be using a Postgres 16 document in the demo. But if we kind of loop back around to the demo we did before, so the blue elephant vase, and if we talk about our product catalog and product data, so that is going to be our PDF document. And what the RAG workflow will do is it will break the document down into chunks. And this is kind of where some of the science comes in and the art of augmented generation comes in, is you're taking that raw data and you're getting and embedding a large vector from that data. And what you're doing is you're storing that data in your database. In our case, it's going to be Amazon's Aurora. And what we'll be storing is we'll be storing the vector we pulled out. We'll be storing the chunk of data that vector's come from. We'll be storing the metadata where the data was actually originating from. So in our case, PDF document, and also an ID column in the table. So Next stage to how embeddings are used is the user itself, the user asking a question. So how much is a blue elephant vase? So this is going to be the question, what comes in. What we do is we take that question and we pass that into our embedding model, the same embedding as we stored our catalog data. And what happens then, that converts that into a vector, which will then, what happens is something called a similarity search. Against the vectors in the database, we have an index on our vectors. Giorgio will talk more about the options you've got in that space as well. And what you get is you can get the question, the context, passed back to a large language model. In our case, we're going to be using Claude 3 Haiku. And what you get back is a response, a human response to the user, as well as the context of where that response has come from. What was the metadata? What document did it come from? What was the source of the data? And also, what was the chunk of data it was taken from? Or if there's multiple chunks, what are the multiple chunks of data? So let's see this action a little bit now. So we have a Postgres database, Postgres Aurora database already pre-created. And we're going to work through the workflow in real time of building this environment. So what we have is quickly just show the configuration. So we have a Postgres 15.6 database. And first thing we're going to do is enable the data API against that database. So this is so Bedrock knowledge bases can talk to our Aurora database. While that's enabling, it takes a minute or so to enable that. While that's enabling, we're going to connect to our Postgres database and we're going to configure our extension, our PostPG vector extension. So we just happen to be using Cloud9 here. ID is just easier in the browser. And really what we're looking to get is a P-SQL prompt so we can connect to our Postgres database. And once we've got our connection to our database, we're going to actually create the extension in the database. We're going to create a table to store our embeddings. And we're going to create an index on our embeddings as well, our vector. So you can see that we've created the table and the index, and we'll reference to these when we go to Bedrock in a moment. So we'll quickly just go over to Bedrock now. And what we're going to do is just enable our model access. So you've got access to multiple models in Bedrock. So you can see some of the models are already, access is already granted. So we've already pre-granted some access. If you need to enable access, you do modify access. You then choose the embedding models you would like to use, foundation models you like to use, click next and accept the license agreement, and you're good to go to use those in Bedrock. So we can now see that the data API is enabled against our Postgres database now. So we're good to go with Bedrock connecting up to our Aurora Postgres database. So what we're going to do now is go back to Bedrock and we're going to go to knowledge bases in Builder Tools. And we're going to create our knowledge base. So we'll click create knowledge base and we'll give our knowledge base a name, call that what you like. We're just calling it PG test KB. And we're going to create a service role. You can use a pre-created service role if you're pre-creating your IAM roles. In this case, we're going to be creating one. We're going to point it at our data source. So we're going to be using an S3 data source. So you can see that we already have an S3 bucket pre-created. And there's a document in this S3 bucket, which we'll see in a little while. So what we're going to do is select that S3 bucket as our data source. And we're going to click next. Next, we're going to choose our embedding model we're going to use for our vector store. So we're going to use Titan Embeddings G1. And we're going to choose our vector store, what data store we're going to use. We're going to use Amazon's Aurora. And then we're going to select now the credentials for the Aurora database. The first thing we need is the ARN of our Aurora database, the resource ARN. So we'll firstly give that to Bedrock. We'll then supply our database name. So we created the table against our Postgres database. The table name was public Bedrock KB. And next thing we're going to give it is our secret to connect to the database. So we store in our passwords in Secrets Manager for the database. So we're providing that on so Bedrock can connect securely to the database. Next, now we're going to provide the field names for the table we created earlier. So first of all, the vector field, the embedding field, then the chunks field, then the metadata field, and then the primary key. Now, what we'll show here is we'll just show the mapping between the two in Cloud9. We'll go back to Cloud9 and we'll quickly just show how the table maps in Cloud9 to what you've got in Bedrock. So really the key point here is call that table what you like, call the columns what you like, as long as you map them over into your Bedrock so they map up the same. So you can see we've got embedding, chunks, metadata, ID, and how they map over into our knowledge base. So that's all the information you need. Now we can click create knowledge base. This will take a minute or so to create, a minute or two to create if you're using a pre-created database. If you're going to use a starter database, the starter database is open search, it takes slightly longer. So we're just showing the document in the S3 bucket here. This is the document we're going to pass through the workflow for retrieval augmented generation. So the knowledge base is created now. First thing you've got to do is sync up your data store. So the process of syncing your data store is the process of the RAG workflow. So it will grab the document, it will break the document down into chunks. For each of those chunks, you will get a vector. So it's stored in embedding our database, and you will have the metadata. So once that area is sunk up, so you can see that sync took quite quickly for us because it was just one document. If you've got multiple documents, it could take longer. So once your documents sunk up, what you can do is choose your foundational model. You want to ask some questions against your knowledge base. So we're going to be using Claude 3 Haiku. And we're going to ask a question. So describe how PG Stat.io views tracks. And what we'll get is information from our knowledge base on our Postgres 16 documentation. You can see the source of the data. You can see the chunk where the responses come from. And you'll see the human-like response. So what we'll have a look at now, we'll have a look at the backend database, our data store, and we'll take a look at what does this look like, this document we broke down. How does it look like in the database? So we can see that PDF document has been broke down into 119 chunks, and we'll take a look at one of the rows in our table, just to have a look at one of those chunks and what does it actually look like inside our database. So we'll go through each field. First of all, you've got the metadata field. So where's the document? Where's it come from? Then we've got the chunk of data. Then we've got the vector ID itself. So this is where the kind of magic happens with the vector itself. Computers work better with numbers than they do actual text search. And then you've got the ID as well. So for each document you would go through the same process. If we were to add another document in, it would do the same process through, and then you would end up with more rows in this table, and then your knowledge base grows. And then when you're asking questions, it's looking at the data and using the vectors to use a most similar search. And Giorgio will talk a little bit about that in more detail when we dive into vectors itself. But the idea of being able to get up quickly and running quickly with a RAG workflow, knowledge bases can rapidly speed up that process and really let you focus in and start looking at how RAG potentially can help your organization. How can you really start looking at developing knowledge bases? How can you get some value out of it without having to worry about how do I actually, do my chunking? How do I pass it through an embedding model, and write the code for this? It can really get you running quite quickly. So that's the end of the demo. So we've got a link for the demo here. I'll just pause slightly and just leave that on the screen if you want to take a quick screenshot of it. It'll be available afterwards as well for you to consume. This is being videoed, so you have access to be able to take a look at this. As I've said, you can go through it in your own account. It has step-by-step on how to do all the steps we've done, or you potentially can reach out to your account team and we can look to do a session with you if you're interested in learning more about Postgres and knowledge bases and vectors. So Let's move on to our next bit of the session, really, which is now Postgres as a vector store. So why would you use Postgres as a vector store? So I guess a couple of things. Postgres is open source. It's been around for a while now, 35 years plus. It's not controlled by a single company. It's controlled by a very large community. It's consistently evolving, to support enterprise workloads. And Giorgio will talk about some of these features, what we have in Postgres Aurora as well when it comes to PG Vector. But one of the most powerful things is the capability of being able to extend Postgres, this thing called extensions. And that's what PG Vector is. PG Vector is an extension, and it gives you the ability to add capabilities onto Postgres without having to change the source code of Postgres, which means you can be really actively developing that extension. So we have core developers of that extension working in AWS. Giorgio will mention some names later and share some links. But the way PG Vectors has evolved over the last year has been quite astonishing, really, with the improvements what's been put into it. And some of the blogs what will be shared, you could go and take a look at it and see some of the performance tweaks you can do with PG Vector and some of the capabilities we have in Aurora as well to really get you to very, very large data sets for your vectors knowledge base itself. So I'm going to pass you on to Giorgio now, who's going to start talking about PG Vector in more detail and diving a little deeper into PG Vector itself. So thanks, everyone.
Thank you, Tony. Thank you so much. I share my presentation. Okay. So exactly, PG Vector is an open source extension that add to a vanilla PostgreSQL database the similarity search and vector data store capabilities. But let's see in detail what does it mean. It add first of all a data type, the vector data type. A vector is a numeric array defined on n dimension, and each dimension is a float data type. So it's a numeric data type that consumes 4 bytes. And the magic is that this numeric array, when is produced by an embeddings model, it contains also the semantic meaning of a piece of information. It also provides the support for 2 vector indexes, IWF flat and HNSW, that we will see in detail, and it brings the ability, leveraging on these indexes, to execute also an approximate nearest neighbor search, together with an exact nearest neighbor search. And Postgres also acts as a metadata store. We have seen in the demo presented by Tony that you can create a table, and in the same table you can store both your generative AI data, so your vectors embeddings, together with metadata and transactional data. And this is much more efficient because allow you to access the data without the need to synchronize different information between different systems. And finally, you have the choice of distance operators. Here are represented 3 instance operators. The first 2 are the most common. There is the Euclidean operator or linear distance. It's the linear distance between vectors. The second one is the cosine operator that represents the angular distance between vectors. And the third one is the inner product. Okay, but let's start introducing the recall concept. When you execute a similarity search, the recall is a measurement of the relevancy or the accuracy of the result. So if you want a recall of 100%, it means that you are retrieving the most accurate results in terms of similarity. And to do that, you need to execute an exact nearest neighbor search. So you have to compare your input vector with all the vectors present in your data store or in your table, dimension by dimension. And as you can imagine, this operation, if you have millions of vectors with thousands of dimensions, is time-consuming and resource-intensive. And for this reason has been introduced the approximate nearest network. The approximate nearest network leverage on vector indexes to reduce the scope of the required comparison, improving the performance from one side, but on the other side, returning a less accurate result. So when you execute an approximate nearest neighbor search leveraging on vector index, the recall will be less than 100%. But we will see now in more detail how you can use the different vector indexes to execute an approximate nearest neighbor search. Okay, let's start from the first index type, that is HNSW, that stands for Hierarchical Navigable Small Word Index. In this case, it's a graph-based index built on multiple layers, and each layer has an increasing density of vectors. When a similarity search query is executed, the input vector is compared with the vectors in the highest layer, and then it transits to the next layer, where are present more vectors to compare, till reaching the last layer and returning the closest result. In this case, the index is iterative. It means that you can create the index on an empty table, on a vector column, and when you keep inserting or updating new index, new vectors, this index is automatically updated. The overhead to insert new vectors in a table with this index is proportional to the size of the index itself. But let's see through this cool animation how it works. So as I mentioned before, when you create the index, the HNSW algorithm keep building a graph on different layers. In this case, I represented 3 layers. As you can see, the vector density moving from the top to the bottom increases. And the nodes of the graph represents the vectors, and the link between the nodes are the distance between vectors. And when you execute a similarity search, in this case, the query vector is the yellow one, the graph is traversed, starting from an entry point in the higher layer and moving till to the bottom layer to retrieve the closest result, in this case the red node, so the red vector. You can compare this kind of algorithm to a Google Map search. You start from the country, then you zoom into the region, then the city, and finally the streets to find your input address. Okay, well done. But let's see how we can influence the recall. As we have explained before, you can use this index to execute an approximate nearest neighbor search. And you have also the capability to influence the accuracy of the result, leveraging on 3 parameters. The first 2 parameters are configurable during the index creation. The M parameters represent the maximum number of connections for each vector at each layer. Instead, the EF underscore construction represents the number of vector candidates that will be evaluated during the index creation. Then you can also configure a parameter before executing a similarity search query, the F underscore search parameter, that represent the number of vector candidates that will be evaluated during the similarity search. But let's see it with an example. In this case, we are creating a table similar to the table created by Tony during the demo. There is an embedding column data type vector defined on 1536 dimension. That is the same number of dimension that is returned by the Titan embeddings model. And on top of this column, we are creating an HNSW index using the vector cosine operator. And we are specifying the parameter m equal to 16 and ef underscore construction equal to 64. After the index creation, we can execute similarity search. And before executing the query, we can specify the parameter ef underscore search, in this case equal to 40. And as you can see, when we execute the approximate nearest neighbor search, we have to specify the same distance operator used to build the index, in this case the cosine operator. And we will use the construct order by limit 5 to retrieve the 5 closest result to our input vector $1. So you can tune and increase this parameter in order to have a better recall. But keep in mind that there are some trade-offs. So increasing this parameter, you will have a better accuracy. But on the other side, you will consume more resources in terms of memory, CPU, and storage. And also, you will have a higher response time. You will need more time to execute your query. So the latency will increase. Okay, but let's move now to the second index type, the IVF flat. In this case, the name is inverted flat file index. It's not a graph index in this case, but it is a k-means index. The k-means algorithm partition and group your vector data space into clusters, also called list. And when you execute, and for each cluster, for each list, the algorithm compute a center or centroid. And when you execute a similarity search, your search vector is compared only with the centroid for each cluster. And the comparison between the vectors is only inside the cluster with the closest centroid. So using this algorithm, you are able to reduce the scope of your similarity search. And to create this index, it's important to know that you need the vector still into the table, because the algorithm must be able to compute the centroid. And the insert time of the new vector is bounded to the number of the list or cluster, not to the size of the index. But also in this case, let's explain how it works with an animation. We have your bunch of vectors into the table. And when you add an IVF flat index, the vectors are partitioned and grouped into clusters or lists. In this case, we have 1, 2, 3, 4, 5 clusters. And as you can see, for each cluster is computed a centroid. And when you execute a similarity search, your query vector is compared only with the 5 centroid. And only the vectors that belong to the cluster with the closest centroid are evaluated to return the closest result. In this case, will be evaluated only the vectors inside the green cluster. And also for this index, it's possible to configure some parameters. There is, you can configure the number of lists when you create an index. So you can specify the number of clusters into which you want to partition your vector data space. And before executing a similarity search, you can specify the number of probes that represent the number of lists to search during the query. For example, in the simple example that I showed you before, the number of lists was 5 and the probes 1, because we only consider the cluster with the closest centroid. And let's see the same example. we have the same table that we used before, but in this case, we are creating an IWF flat index on the column embedding. And we are using again the vector cosine operator. You can see here that we are specifying 500 clusters or list. And before executing the similarity search, we can also specify the number of probes. So we would like to compare only the vector belonging to the 20 clusters over the 500 cluster with the closest centroid to our input vector $1. Okay, well done. But which search method do I choose? So if you want a 100% recall, what you have to do is to execute an exact nearest neighbor search. So in this case, you don't need an index at all. Instead, if you want to increase the similarity search performance, you can use the approximate nearest neighbor search. And if you are looking for a fast indexing that consume a few resources, IWF flat is a good starting point. But if you prefer an index that is easy to manage and it also provides with the default value a good ratio between performance and recall, HNSW is the best solution. And for this reason, many generative AI application developers as a starting point prefers this index. Okay, well done. But now that we have seen how similarity search works, we can move on and discuss how Amazon Aurora can boost your generative AI application, leveraging on Aurora native features. Aurora, as you probably know, is an AWS cloud native relational database service with MySQL and Postgres compatibility, and it's also compatible with pgvector extension. And Amazon Aurora provides high performance and enterprise-grade scalability and availability. But let's start from the first feature, that is I optimize with optimized read. This feature leverage on local attach and NVMe storage that are available on certain instance types to provide two features. The first one is an additional layer of cache that leverage on local attached direct disk to keep much more data near the database instance. And the second feature is the capability to spill the query that don't fit into the memory, in the work area memory, for example, query that has to execute a huge group by, sort, or joining operation. This query will be split not into the EBS block volume, but into the local attached disk. And this disk provides a very high throughput and very low latency. So this feature enables you to execute the query with a very low latency. The second feature is the compatibility with Amazon Bedrock. We have already seen with Tony how Amazon Bedrock knowledge base supports also Amazon Aurora as a vector data store. And in addition, you can also access directly from your SQL code the foundation model available through Amazon Bedrock directly from SQL code using the leveraging on AWS underscore machine learning extension. We will see an example later on. And Aurora Postgres supports the pgvector extension 0.7.0 that in addition to IWF flat and HNSW index provides also advanced features as scalar and binary quantization. And finally, Amazon Aurora can scale up and down to handle even the most demanding workloads. Okay, but let's see a couple of benchmark to better understand the improvement that are offered by these features. In this example, we are comparing an Aurora cluster with the optimized read feature enable, the yellow one, with an Aurora cluster without this feature enable. In this case, we are using a big ANN benchmark, that is a billion scale approximate nearest network search benchmark, using a dataset of around 1 billion of vectors and an HNSW index that provides a recall of 96%. As you can see here, increasing the concurrency up to 96 client, you can see that the performance of the Aurora cluster with the optimized read feature enable can increase up to 9 times compared to the Aurora cluster without this feature in terms of query per second. In this case, we are executing a similarity search query that does not fit into the memory, so needs to spill to disk. And with optimized read feature enable, they can leverage on direct attach local storage. So the takeaway here is that this feature can improve a lot the similarity search query performance. In the second example, we are using the same benchmark, but in this case, we are comparing two Aurora clusters with different processor generations. The first one is a Graviton 2 provided by R6G, and the yellow one is a Graviton 3 provided by the instance class R7G. And in this case, we are executing a similarity search, increasing the parameter EF underscore search. Do you remember when you increase this parameter, you can improve your recall, so you can obtain a higher accuracy of your result, but on the other hand, you will consume much more resources, and also the response time of your query will be higher. And when we reach 800 for this parameter, so a very high recall value, we can see that the gain, the speed up of the Graviton 3 compared to Graviton 2 is up to more than the 60% in terms of transaction per second. So also the right choice of hardware does really matter in terms of performance. And finally, let's see an example of integration between Aurora Postgres and Amazon Bedrock. In this case, we have a cluster with the AWS underscore machine learning extension configured. And in this way, you have the capability to leverage on two API to access the foundation model available through Amazon Bedrock. The first API is AWS underscore bedrock dot invoke underscore model underscore get embeddings to convert into vectors a piece of information. And the second API is the invoke underscore model. For example, here we are calling through a SQL query the invoke model API in order to query the Titan Text Express v1 foundation model, providing an input text, this one. And the model, we will return you an answer in JSON format. This integration is particularly useful in use cases as case note summarization, product catalog search, and sentiment analysis. Okay, well done. And finally, we want to provide you some useful link. If you want to deep dive this topic, here are reported a list of AWS blogs, but we have also added some blogs written by Jonathan Katz. Jonathan Katz is a product manager in AWS for Amazon Aurora, but he is also one of the main contributors for the pgvector community, of the pgvector community. So his blogs are super up to date and very, very interesting. I suggest you to give a look. And finally, if you want to stay up to date with the last feature related to Amazon Aurora, but also to the other AWS service, you can access the AWS News web page. And most important, in the end, if you need help to define your data strategy or simply want to discuss this topic more in detail, Tony, and the rest of our team is available to support you. So if you want, you can reach out directly. And thank you for your attention. And please, we ask you if you can access this survey. It takes only 1 minute of your time, but for us, it's super useful to receive your feedback and to improve this kind of session. So thank you so much. And if you have any question, now me and Tony are available. I think we have a few minutes.
Yes, Giorgio and Tony, thank you for this insightful talk. Yes, we do have a few questions, so let's jump straight into those because, yes, we do have a few minutes for those. The first one is, well, it's a bit controversial, but so the question is the following. Is PG vectors HNSW indexing sufficient for knowledge graphs, or should we switch to a GraphDB like Neptune?
I can go.
Yeah, controversial.
Let me say, yes, HNSW is an index type that uses a graph protocol. But and this is one point. So it's a good starting point, as mentioned during the presentation, because compared with EWF flat index, it is an iterative index. Is it automatically managed? So if you insert, update your vectors, also the index is maintained. Instead, with EWF flat, at a certain point, you will have to rebuild your index because the centroid are not recomputed dynamically. This is one point. Then we have our purpose-built graph database that is Neptune. And also Neptune has the similarity search, the vector capabilities. So it's a matter of conveniences. If you are already using Postgres for your transactional data, probably it's worth to use also Postgres for your generative AI data in order to have all your knowledge base in the same data store without the need to synchronize data between different systems. On the otherwise, if you are already using Neptune for your data, probably you could start from there to implement your retrieval augmented generation workflow because you have already the knowledge to operate on that kind of engine, and also your application are already designed to work with Neptune. You have different choices.
Yeah, exactly. So it's also going to be based on what we have got at this particular moment, what our system has already got.
Exactly, the system you are used to use for your transactional data. So you don't, in this case, you won't have to readapt the application to change the drivers, to learn new skills because you already use you already skill on Postgres, for example, and also this is the reason why in AWS we are adding the data vector capabilities to our major purpose-built databases.
It's probably worth saying
All right,
as well,
thanks.
testing, for, like anything where you're going to choose where you want to store your vectors, try them out is probably your best bet. And if you've got maybe experience in Neptune, OpenSearch, RDS, which one's going to work best for you? But typically your starting point is potentially a data store you're familiar with.
All right, yeah, that's a pretty solid answer. Thanks. Let's jump into a few other ones. Indeed, we've got questions that are, I think, touching different angles of your talk, I would say. This one is a bit more, well, technical, I guess. So the question is the following. So as far as you can see, the lowest floating point precision supported by a PG vector is 16 bits. Have you tried to support a lower precision, such as, well, FP8 or anything similar to those?
One for you, Giorgio. That's beyond me. That.
Yes, it's a very technical question. Probably it's worth, yes, to take it and reply in a follow-up. So for sure. Now, what I want to say, give a look to the links that we provided, especially the Jonathan Katz link, because includes the last innovation. Also, as I mentioned, there is the scalar quantization and the binary quantization that improve a lot the vector capabilities and the approximate nearest network search capabilities. So it's a technology that continue to evolve, and the important thing is to access the right resources to stay in sync. And vet blogs for sure are super useful. Yes, also to see the last innovation for PG vector extension.
All right. So let's cover a couple of more questions. I think that we are on the right track now. So this one, how does Aurora handle replication and flavored in a multi-AZ setup for PostgreSQL databases? So in terms of failover and multi-AZ setup for PostgreSQL databases.
Tony, do you want to?
Sorry, I got loads of feedback there. I didn't really. I can hear someone else talking as well. So I got. Could you just repeat that? Was it how does Aurora handle failover?
So yeah, the question is, how does Aurora handle replication and failover in a multi-AZ setup for PostgreSQL databases?
Yeah, so Aurora's got there's a couple of capabilities within Aurora. You've got just read replicas, essentially, which the Aurora storage engine is a 6-way copy across multi-AZ. So when you've got a read replica connecting to your, so it's not really multi-AZ, it's multi-AZ, but it's not multi-AZ in the standard what you'd see with an RDS database. In the event of a failover, your read replica is talking already to the data, storage, using the same storage layer as the writer. So in the event of a failure, say your instance failed, what was your primary writer? Your reader would now take over as your writer, and your writer endpoints, your application would automatically redirect to the writer. That typically takes, between 10 to 20 seconds. You can speed that up by putting an RDS proxy in front of it, so you can bring that time for failover down. That's how it works with Aurora. Standard RDS is slightly different because the technology is different. It uses, the way we do is, as soon as you take RDS Postgres, it's an actual copy of the data from a storage replication perspective. And in the event of failure, you fail over to the standby copy. They are synchronously replicated, so you don't lose data, but that failover can just take slightly longer, between 60 to 120 seconds. So the two technologies are slightly different, but they do come under the RDS banner, RDS Postgres and RDS Aurora Postgres.
All right. Yeah. So it's.
And if you want to know more, just reach out. You've got our LinkedIn badges. Reach out and we can talk more about that in more detail. We did go into global databases as well. You've got global databases on top of that for Aurora. So yeah, it's quite a large area, to be fair.
And we have also dedicated workshop called Immersion Day, so we can explore in deep detail all the feature. But here, yes, the key point is that Aurora provides a distributed cluster, so a storage cluster, So the storage is by design replicated across 3 availability zones. So it's designed to be high available and high durable, the storage. And then you can configure a read-only instance in 1, 2, or in 3 availability zone, different
You
availability
can have up to
zone.
15 of them, can't you? 15 read
Up to
records.
15, yes, in the same or different availability zone.
It's easy.
I think we can squeeze in one last question. But I mean, it's good that you're mentioning things. We've got actually a bit more questions here. So yeah, it's for our viewers. So if, well, this day we won't be able to cover yours. So from what I hear, Tony and Giorgio, we will be able to then answer some of the questions directly, or then one of our other point to the proper literature to sort some of those questions. So then the last question that we're going to cover is the following, which is also a bit on the technical side, I would say. But can you perform hybrid queries combining IVF flat vector searches and relational data filters in PostgreSQL?
Sure, this is one of the big advantage to have the transactional data together with the generative AI data, because you have the capability also to join different tables and also to filter on different columns, also on the transactional data columns, not only on the vector columns. So yes, it's possible. And also in this case, there is a new blog. I think we can share the link later on. Yes.
All right, thank you so much for answering these questions. Is there any question in particular that you remember and that you liked, so we can give a little present to the person who has asked the question?
I liked the
some of the
multi-AV
questions?
one because it was easy enough to answer, but really we should give the prize to that super hard question. What was that was asked?
So you're referring about the PG vector and the precision then, so about 16 bits. And if you
the
try
one
the
what was a bit
FP8.
challenging for us, where we're like, yeah, we do need to come back to you on that one. So yeah.
Yeah, definitely. Yeah, I think I agree upon that, because it's quite a good one.
Now, another interesting question that I have already a bit anticipated is about the fact that if we have flat index, at a certain point need to be rebuilded if you keep executing a lot of data, DML, data manipulation language operation. So if you execute a lot of insert, update, deletes, the index is not updated, so you have to rebuild it. And this is an important point to take in count when you use this kind of index. It's a better choice is if you have a stable data set that does not evolve during the time, but is pretty stable. Otherwise, it's better HNSW index.
Right. All right. With that, I think we can say that the question from Henry has won. So please contact us through the email that you see in the chat, and the organizers will let you know how to receive your gift. But yeah, Tony, Giorgio, thank you so much, guys, for this insightful talk. We did enjoy this a lot and learned a ton, that's for certain. So thank you.
Yeah,
Our
thanks
pleasure.
for having us. It was a pleasure to be here.
Thank you so much. Bye all.
Bye.
Yes.